This is Dr. Harris, and I'm going to talk with you a little bit today about analog inputs for our Arduinos. There are two different kinds of inputs that are possible on an Arduino, and one of them is digital, and we have some experience with digital whenever we were dealing with blinking an LED. So with digital, either something is completely on or completely off. So that means it's either connected to, in our case, our Arduinos are 0 volts or 5 volts. And when we were dealing with our LEDs, if I wanted to turn an LED off, I would say digital right, and then I would tell the pin the LED is on, and then I would say digital right, pin whatever, low. And whenever I say that, what I'm really saying is connect pin 13, for instance, to 0 volts. So have 0 volts on that pin. And the LED shouldn't turn on. Then, if I want to turn the LED on in our blink program, I say digital right, whatever the pin is, so for instance pin 13, and I would say high. And when I say high, what I'm intending it to do is to actually output 5 volts. And so there's nothing in between here that's a valid state in a digital output. I'm either all the way off or I'm all the way on. And in fact, LEDs work in this fashion. They are either lit up or they're not lit up. And we'll talk about that more in another video. However, this is the basics of digital. So if I had a digital input, what I would use instead of digital write, I would say digital read. And I would tell what pin I'm trying to read. So for instance, if I had a button connected such that most of the time the button is connected to 5 volts, but when I push the button, it opens the switch of the button. So a button is literally just a area in the circuit that has this piece that I can either push or well, I push and it either connects or disconnects a piece of the circuit. So therefore, current can't flow through this open circuit here. It's not connected. But if I push the button, then it closes the circuit and current is allowed to flow. Now, on an Arduino, usually what we have done is we have one end that's connected to your Arduino. So this goes to my Arduino pin, and this side might go to my ground, which is my 0 volts, and then I have what's called a pull-up resistor, which I drew it on the bottom, but it's a pull-up resistor, and it is connected to 5 volts. And in fact, this pull-up resistor is built into the Arduino, and we can talk about that later as well. However, if I'm doing a button in this fashion, then all the time that the button is not pushed, I'm getting a digital high on that input. And then when I push the button, what happens is it connects this ground to the Arduino input. And so that gives me a digital low. And so in this fashion, I can read an input of a button, and I can compare that to high or low to see whether or not my button is pushed or not pushed. And then I can use an if statement to determine what function I should have when the button is pushed. For instance, when the button is pushed, I want the LED to come on. When I don't push the button, I want the LED to be off. So that's a very simple if statement. Now, this is digital input here. But I mentioned in the beginning of this video, we're actually talking about analog input today. So, what is analog input? Analog input is some input that doesn't just take a full 0 to a full 5 volts. It actually can take multiple values in between. So, we can actually measure this at different points and say, okay, well, this is the input that I'm getting is some voltage in between 0 and 5 volts. Now, how is this useful? Why would we want to use this? Well, most phenomena in the universe that we can measure with simple sensors are they're analog in nature. For instance, if I have a cup of cold water at 0 degrees Celsius, let me draw that a little better. So I've got this is frozen water, and then I want to boil it at 100 degrees Celsius, and then I want to just, as soon as I reach the boiling point, just stop adding energy and just let it cool down. So what I would get is I would get a graph that looks something like this, with this axis being our time. And so at any point in this graph, I can take a measurement. So if I look right here, let me get another color here. If I look right there, I measure this in, and I say, well, this looks at like 25 degrees Celsius. And then if I look right here, this looks to be about 50 degrees Celsius. And if I look, let's go ahead and look at this one. So this one looks to be at 100 degrees Celsius. And so here you can see I don't just go immediately from 0 to 100 degrees. There's this slow ramping up. So my voltage, it's important that I have this ability to read analog values, because maybe I'm doing a thermostat that's supposed to control the temperature of the water. So I get about 25% of the maximum, about 50% of the maximum, and then this is about 100% of the maximum value at these different times. Now I can do something with this information. So if I look here, I'm getting not 100% of my voltage. I'm getting, well, in this top one here, this is 100%, so this is 5 volts. So then if I look, this is about 50%. So that should be giving me about 2.5 volts. And then I have about 25%. That should be giving me about 1.25 volts. So I'm going to get a variety of voltages on my input. And that allows me to do things like multiple if statements, or even what's called a case statement, so that I can say if the voltage is somewhere between 1.25 and 2.5, maybe I don't necessarily want to add all this energy to continue boiling the water. Maybe I want to keep the temperature at that point. So what I would do is I'd say, okay, after I get from here to here, I wanted it to heat up at 100% speed that it can possibly heat up. But then I want to make sure that it stays within this range. So I could turn on the heater and then turn off the heater over and over again. So it's not quite boiling and it's not quite cooling down all the way. It's just getting a nice warm temperature. Maybe this is a little coffee pot or coffee cup warmer. So basically I can constrain my output to turn on and turn off my heater element based on this analog input that I'm reading. So whenever you read an analog input into an Arduino, what it actually does is it takes the values of 0 to 5 volts and it splits them up into a number between 0 and 1023. Now 1023 is not an arbitrary number. This is actually due to the fact that we're using a memory element that has a certain number of binary digits that it can represent numbers in. So what I'm going to do is I'm scaling my 0 to 5 volts to a range between 0 and 1023. And so let's say I have approximately, if I had the same input here, the same kind of hump of readings, we can say that at approximately 25% of my 5 volts, I was getting 1.25 volts. Well, that's going to be 25% of this value, which is about 127. And then if I look at my 50% mark, that's going to give me 50% of this number, which is about 255. And so I can do the same thing, just unit converting between my 0 and 1023 and my 0 and 5 volts. And this allows me to read an input. Now, this is a useful tool whenever we're dealing with, as I mentioned before, some kind of sensor on our input of our Arduinos. One of the first sensors that you'll notice whenever you start playing with your SparkFun Redboard kits that they suggest you use is called a potentiometer. And a potentiometer looks like, let's find it here. It looks like this. It's a blue knob. And this blue knob has 3 pins. And if you look here, this is the actual schematic of the way you should hook this up. We have 1 pin on the end here that we're going to connect to 5 volts. On the other end, we're going to connect it to ground, and then the center is called our wiper. And we're going to use that to go to our analog inputs over here. So that's how the circuit looks on the Arduino. What does the circuit actually look like? Well, if you would recall, we had discussed a circuit in which we have a power source and some series resistors. And we were able to calculate, given the values of these resistors, we could calculate the voltage across each resistor. We were able to do that by breaking this into a single resistance, converting this into a single resistance, and then finding Ohm's law allows us to find the current, and then breaking it back apart, and then using Ohm's law then to find our voltage across any particular resistor. There's actually another and an easier method of doing this, and it's called the voltage divider rule. And what we could do is we could take our V total here, which is 5 volts, and we're going to find, actually let me do this. So we got V total. We're going to find the ratio of how much of the voltage drops across this resistor versus how much voltage drops across both resistors. And so the way that we do that is we take, if I want to find V2 for instance, I will say V2 is equal to, I'm going to take the ratio of the resistor 2 value over the total resistance. And this is going to give me the value of the voltage across just this one resistor. And that's very useful. So, for instance, if I have a value of R1 is equal to 5k ohms and R2 is equal to 5k ohms, what I would get is 5 volts times 5k ohms over 10k ohms, which will give me a voltage of 2.5 volts. Now it's important to keep your units here. So if you notice, I have my my kilovolts or kilo ohms here. Kilo ohms cancels with kilo ohms, and this is a raw ratio of 1/2 times 5 volts. So that makes sense that I would get 1/2 of 5 volts there, right? 2.5 volts. So I would read in this 2.5 volts, but it would go into my Arduino in a scale of this ratio times 1023. So this would be 5 over 10, which is 1/2, and that gives me approximately 512 units. And we're just going to call these units or steps, for instance. So I'm going to get approximately half of this value here. Now, that's good for a perfectly balanced voltage divider. But what happens when we have something that's not so balanced? What happens if I have the same schematic, however, I have 2.5 kilo ohms on top and 7.5 kilo ohms on bottom? And I have my still 5 volt signal here. So what is the value of my V? I'm going to call this V out. Well, I take 5 volts because I'm doing voltage divider, so V total is equal to R2 over R1. Oh, sorry. That's not equal to, that's multiply here. And so this is V out is equal to V total times R2 over R1 plus R2. So this is 5 volts times, this is 7.5 K ohms over 10 K ohms. And it's 10 K ohms because it's 2.5 plus 7.5. So this gives me about 75% of 5 volts. So what would that be? Well, if 50% of 5 volts is 2.5, and then 50% of that is 1.25, then this should give me 3.75 volts. And so that's approximately 75% of 5 volts. Well, what would be 75% of 1023? Because that's what my Arduino is actually going to see. So 7.5 over 10. So this is going to give me approximately 767 units. And so I can equate this, again, back to this voltage, and then depending on what this is giving me, I can know how many units I'll get. Well, this is useful because I can replace this resistor with a sensor. And so instead of using a regular resistor, I can use a photoresistor or a flexible resistor or a soft potentiometer, something of that sort. And so I can measure the amount of flex, the amount of pressure, the amount of light, you name it. And I can use these kinds of calculations to make sense of that data. Now, the way that the light sensor, for instance, would work, it would tell me maybe how many lumens I'm going to get for a certain resistance value. And I can use a reference resistor, like this 2.5K here, and calculate the voltage, or measure the voltage rather, and then backwards calculate what this resistance is, and then that will tell me the number of lumens. Well, inside the Arduino, I don't actually get this voltage, I get this number right here, the units. So I would have to take the units, convert that into voltage with a simple unit conversion, and then take this unit conversion from the voltage, go back to calculate my resistance of the R2 value, and then know what this resistance value is, and then another simple unit conversion to get the number of lumens that sensor is reading. Now we can simulate this pretty easily using a potentiometer. So I mentioned the potentiometer before has 3 pins. We've got pin 1, pin 2, and the wiper. Actually, I'll say this is pin 3, and then this is pin 2, and that will be our wiper. And it's called a wiper because it literally moves up and down this resistance, and it's touching a certain portion of that resistor. And so the resistance from 1 to 2 can change, as well as the resistance from 2 to 3. However, the total resistance from 1 to 3 stays the same. And in our kit, we have a 10K resistor. And so, if you noticed, my two examples before were total resistance was 10K. So, if I were to connect this up such that I could read the input with my Arduino, I have my 5 volts, I would have my potentiometer, and so our total here is 10K, and then I have my wiper, so maybe this is pin 1, pin 3, and my wiper on pin 2 will be the actual output to my Arduino pin. And this will be an analog pin, by the way. And so what I can do is, if I have my wiper at approximately 50%, my knob is turned approximately 50% between each maximum value I can have, then I'll have half, or 50%, of my resistance from 1 to 2, and the other half from 2 to 3. And so I'll get a voltage of approximately 50%, the maximum voltage here. And so that's the same thing as if I had the 2 resistors, each being 5K, and I measured the voltage out here. If I then turn my knob such that the 2 is closer to the 3, I might get maybe 25% down here and 75 up here. Well, since the total is 10K, then that'd be 7.5K on top, 2.5K on the bottom. And if you wanted to go back to our example, we could do the inverse of that. We could have 25K on top and 2.5, and 7.5K on bottom. And then we will modify what we were modeling here, and we can measure our V out, and again we were measuring that to be a voltage, but then that voltage gets converted into some number between 0 and 1023. So the Arduino itself is actually going to read in the number, and I did that backwards actually. I've got 2.5K should be on top. There we go, and then 7 should be on bottom. And so the value that we read between 0 and 1023 inside the Arduino would give me 767. So I would read this value inside my Arduino. I would want to convert that probably to the voltage calculation. So I would take what is the ratio of 767 over 1023. I multiply that by my total resistance here, 10K. I can measure that resistor, or I multiply it by the 5 volts, and that will measure the voltage out. So this is what we're actually doing in one of the labs here for the Arduino. We're going to measure the value of this resistance, and then we're going to flash this LED on and then off, and the delay is controlled by the value that we read in here. And since this reads in from 0 to 1023, we just put that number, 0 to 1023, whatever it reads in, into our delay function, because our delay does milliseconds, and 1023 milliseconds is just over 1 second. So we can go down and look at the code here. How do we set this up? Well, we have 2 pins. Our sensor pin is an analog input on pin 0, and our output, we're going to have our LED pin on pin 13. In our void setup, all we have to do is set our LED pin as an output. We don't have to really tell it anything about the analog inputs, because those are assumed they're analog inputs. That's why they're on the other side of the board. Then in our loop function, we're going to make an integer variable to store the value of our sensor value. And then we're going to say sensor value is equal to analog read sensor pin. So this takes the reading from the sensor pin, and this will be that number between 0 and 1020 and 23. Then it's going to turn on our LED and delay for whatever that number was, from 0 to 1023, depending on where our knob is located. It's going to then turn the LED off for that same amount of time. And so this happens super quick, this loop, and that's the end of the loop here. So that loop happens over and over and over again. And as it happens, we can turn the knob and we can adjust the frequency that the light is flashing. So that's our basic analog input. Now, I mentioned again, we don't have to use a potentiometer. We could use the soft potentiometer or the soft pot. And there's actually a tutorial here that says how to use a soft potentiometer, experiment 10. And this is using our soft potentiometer. So you can put your finger here and slide it up and down on this conductive portion here, and that will change the potentiometer just like turning the knob. So we would connect this up in a very similar fashion, except they are putting a extra resistor in here, probably because this is a low resistance. And so we're going to read that into our analog output. And what they're doing differently here, this is using the RGB LED. So this is actually 3 LEDs in one. But you can do the same thing if you did your soft pot in place of your potentiometer in the other circuit. And so that's the basics of analog input. Again, you could also read a photoresistor. And so this is a photocell, and the resistance changes based on the amount of light hitting that photocell. And so if we replace our potentiometer with this photocell and a reference resistor, and again that would look just like this part. This is our reference resistor and this would be our photocell, for instance. We can use the same code as our potentiometer. We read in my analog 0, and then I'm going to flash my LED at different frequencies. And so try these out. Basically just put your soft potentiometer in series with a 1K resistor and connect that in place of your potentiometer on your Arduino to look like this. And usually when you have a sensor, you'll have a symbol to reference that there's a sensor here, and this has a light input. And then you should be able to get similar kinds of functions on your LED based on how much light is coming into that photocell. So you can put your hand over it to make a shadow and see if that changes the value, and you can actually calculate the number of milliseconds that you expect it to go on and off based on the resistance of that photocell. So that should be it for analog inputs. The next video will discuss analog outputs, which are a pretty useful tool as well.